Angela Rasmussen from the Department of Electrical and Computer Engineering at the University of Utah, and I'm going to go over now a DC analysis example. So this is the circuit that we're going to look at here. So we want to find IB, IE, IC, and then the voltages VB, VE, VC, and do approve or disprove the operation for the active region. So remember, the active region condition is when the voltage at the collector is greater than the voltage at the base. So here, that is a very big dot. So here would be the collector, and then this would be my base location. So the first thing that you notice is that this is a little bit more complicated circuit at the base location. So we're going to disconnect it at the base and take a Thevenin equivalent of this portion. The capacitor for DC, remember, DC is omega equals 0. And so if you look at the impedance of that capacitor in DC, it's going to look like an open. 1/0 is an open. So we're going to open those up for the DC analysis. For this circuit, I'm going to copy it and use this as the circuit to find the Thevenin. So we need to find RTH and VTH. And as you notice, when you disconnect this, the nice thing is that there's no current going to be flowing. So this is going to look like an open and disconnect also from that side of the circuit. And so we're left with a little bit simpler circuit here. So there's not going to be any current flowing in this branch, which is really nice. Sorry about that. So we don't have any current flowing in this branch, so there's no current there. VTH is going to be at the end of this. And if I can find the node here, which looks like a open there, the node here, if I can find the voltage there, then it's going to be, if I call that Vx, VTH will be Vx plus 2 volts. So you would go across that. So Vx is 1 voltage and then another plus 2 volts to get to VTH. So I can do a node voltage, or I can do a voltage loop here. If I do node voltage, in this branch I'll have 10 milliamps, and in this branch I'll have Vx minus 3 minus a minus 5 over 100. So I have plus 10 milli, and then Vx minus 3 minus a minus 5 over 100 equals 0. And I can solve this for Vx now. And I would get a minus 10 milli goes over to the other side. I multiply it by 100. And then I'm going to take the minus 3 over to become plus 3. And then the plus 5 will become a minus 5. And so multiplying that out, I get a Vx, or VTH will be this Vx value. So I have a minus 5 plus 3 is a minus 2 minus 10 milli times 100 plus 2. And then that leaves me with a minus 1 volt. So this is my VTH value would be minus 1. And then to look at the RTH, I'm going to open up, a little too big. I'm going to open up this current source. So that 2K now becomes floating, and I'm going to have the voltage sources will become a wire. And so this will be a wire, and then this will wire, and then that goes a wire to ground. So my only path there is through the 1K. From here to ground is the only pathway, and so RTH will be 100 ohms. So I'm going to use that in this circuit. So I'm going to create, I'm going to replace this more complicated circuit now. So I'm going to do green with that RTH and VTH. So just give me a second to replace. So this whole section is going to be replaced by the RTH and VTH. And it will go into the base. And so I have the -1 volt and then the 100 ohms. And then this current is IB, which is going to go plus to minus. I also know I have a 0.7 volt drop here. And then the currents through here will be IE. So this will be plus to minus here, and then a plus to minus here. So as I take, again, when we solve for the DC, we're going to take a loop from the base to emitter. So this will be a minus, 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 and then this will be a plus 15 volts. And so my loop here I'm going to write that out. So I get, it was a -1. So I have -1 minus IB 100 minus 0.7 minus IE, and I can add up the two resistors. So that would be 2.75K, and then a -1 and a plus 15. And that will be equal to 0. And then I'm going to use the relationship of IB and IE. So IB is equal to IE over beta plus 1, and beta was given as 100, so 101. And then I plug that in for the IB here. And I get adding up the -1, -1, minus 0.7, and plus 15. 15 minus 2 is 13, minus 0.7 is 12.3. So I get 12.3. And then I have IE is equal to 12.3. And then it's going to be 2.75K plus the plug-in for the 100 over 101. And that will give me a value of IE to be 4.5 milliamps. So that's my IE value. I can then plug that back in for IE here for IB, and I get 44 microamps. And I can use the relationship for IC, which is beta IB, or beta over beta plus 1, which is alpha IE. And that gives me 4.4 milliamps. So now I have all three currents, and I want all three voltages, VB, VE, VC. So to get those, I have VB, which is here, is going to be a -1 minus IB 100. So a -1 minus IB 100. So using that IB, I get a value of it's approximately -1, because IB is so small. And then VE, you can either take this -0.7, so VE would be minus 1.7 volts, or you can take the loop down here, which would be, you would go up, so -15 plus 2.75 K IE plus 1, and you should get approximately -1.7 also. And then VC, which is up here, you're going to use the IC value, and VC is 15 minus IC1K plus 1. And so that value ends up being 11.6 volts. So our proof is to say that yes, 11.6 is greater than VB, which was -1. So there's our check to verify that and prove that it is on and in the active mode. So that answers all of the DC values. And we proved that the operating region is in the active mode. And then we want to draw a rough sketch of the collector if the gain is 10 volts per volt between V out, which was VC, over the input Vin. So what that means is if our input, I have to go back, I erased the input. The input was a 400 millivolt amplitude. I'm going to write that down. It was on there, but I erased it. So it was 400 millivolt amplitude. And a frequency of 60 hertz. And so if I have an amplitude of 0.4, and the gain, AC gain, was stated as 10 volts per volt, then I'm going to center it around 11.6 volts. So that was the DC value we found for VC. And so it's going to be centered there. And then our gain is going to be this output times this input. So that's going to be 10 times 0.4 for a gain of, or voltage change of 4 volts. So it will go up by 4 volts and down by 4 volts, centered around 11.6. So it will go up to 15.6 and down to 7.6. So the things we have to check is that, does it hit a maximum voltage due to the supply voltages? So we see here that we get 15 plus 1 volt is going to be our supply voltage. So the max it could go on the VC is 16 volts. And so going up to 15.6 can still within that range. So we're not going to hit a maximum on that. The other issue is VB, and we had VB as a -1, and we see that AC amplification never goes down to as low as -1. So we're not going to have any distortion on this circuit. All right, thank you for watching.